Welcome for joining us for today's webinar featuring Professor Giorgio Spada. The webinar today is being recorded and will be available for on-demand viewing through geodynamics.org. During the webinar, only the host and presenter will have their microphone enabled, so use the chat window like you've been doing. If you have any questions or to communicate with others, or if there are problems with the feeds, please just let us know. Our presentations in this series will be approximately 15 minutes in length, with questions and answers following during the remaining time. There is also a slight delay in the audio and video feed, and more so since Giorgio is joining us from Italy today, so please be patient. Professor Spada received his PhD at the University of Bologna and is currently a professor of physics at the solid Earth at Urbino University. His research spans topics in the physics of the solid Earth, from mantle rheology to long-term Earth rotation. Today, he delves more into the area of global and regional sea level variations and modeling of post-glacial deformations in his use of SELEN, a sea level equation solver developed with Daniele Mellini and now hosted in the SIG repository. So, Giorgio, the screen is yours.
Okay, thank you very much, Lorraine. Hi to everybody. Hi, everyone. I'm Giorgio Spada from Italy, and today, in collaboration with Daniele Mellini from INGV in Rome, I'm going to present the basic features of SELEN, a program for solving the sea level equation, which is now available from CIG. My first slide will be a short summary of my presentation. I will basically have five points. First of all, a few introductory notes about the program SELEN and the basic features of this program. I would like also to address immediately after this some remarks about the theory behind SELEN. SELEN is not SELEN is solving the sea level equation, and the sea level equation is not indeed one of the classical equations in geophysics. So I think that a few words about the theory behind SELEN can be useful for this presentation. I will spend a very short time describing how to configure and to execute the program. After this, I will show in detail the configuration of a test run with SELEN, and we will go through the outputs of this test run, which is oriented to a realistic geophysical problem. So the last part of my presentation will be illustrating the outputs of this test run with the SELEN program. Well, first of all, what is SELEN? Shortly, SELEN, which is an acronym for Sea Level Equation Solver, is a program that solves numerically the so-called sea level equation, which will be abbreviated with SLE in the following. This equation is solved for a very particular Earth model. The model will be a spherical model with a layered rheology. The rheology will be a Maxwell rheology. The model will be non-rotating, so we use this approximation for this version of our program. And in general, SELEN is useful for studying surface loading problems, but in particular, it is oriented to loading problems in which the load is constituted by ice loads and water loads. So it is an ideal tool for solving the so-called glacial isostatic adjustment problem. And since gravity plays an important role in this sea level equation problem, SELEN is also useful for describing the gravity field variations and the changes in the shape of the Earth in response to glacial isostatic adjustment. SELEN has been first introduced in 2007 in a paper on computer and geoscience by myself and Paolo Stocchi, and now it has been greatly improved, and the current version is version 2.9, which is now available from the CIG to all the people interested in global geodynamics, and in particular on glacial isostatic adjustment. So before this seminar, it is assumed that you have at least some familiarity with spectral methods, in particular about harmonic functions and their basic properties, and on the general problem of sea level change. The problem of sea level change is a central problem in geophysics. What we are going to discuss today is a particular aspect of the more general problem of sea level change, which is basically related to glacial isostatic adjustment and on the sea level variations associated with this process of a readjustment of the Earth's crust in response to ice unloading. So I also assume that you have looked at the SELEN user guide, including the very condensed theory, and you have installed the code on your system, possibly. Hopefully, you have also tried to run SELEN following the hints in the guide. And if you did this, it's okay. If you didn't do that, please don't go away. Stay with us until the end. I will go through the user guide and make some example showing how to run the code. So please stay with us. As you know, the official web page of SELEN is this one at the CIG. And if you go there, you can download very easily the compressed archive of SELEN. The file name is this one. This archive contains the source code and the input data necessary to run the program. A list of publication is available from the CIG web page, and this list of publication is useful to understand the potential of SELEN. And you will see that SELEN has been applied quite recently in a number of papers dealing with the glacial isostatic adjustment and other aspects of global geodynamics. So I hope that it will be useful also for you in the future, and it has been designed in a simple way in order to facilitate intercomparison and application to a broad range of geophysical problems, hopefully. So the user guide is available. It is a 60 pages booklet containing some introduction and first of all, a few pages about the theoretical background of SELEN. It goes quite in detail on showing how SELEN is working, and gives examples on the setting up and execution of SELEN. At the end of the book, we have presented a test run of SELEN, which is not the same that we present today. In any case, we will have a full example showing all the possibilities of this program oriented to the study of glacial isostatic adjustment. So the SELEN logo is an artwork of our colleague Florence Colleoni, and on the left, the SELEN logo shows a so-called sea level fingerprint. This map is a pictorial view of the so-called sea level fingerprint associated with the melting of the late Pleistocene ice sheets. So the basic point here is SELEN is solving the sea level equation, and this sea level equation is not predicting uniform sea level variations through the Earth. And the reason is that there is a complex interaction between the ice and the solid Earth. At the same time, there is gravitational interaction between the oceans and the solid Earth, and so on. So SELEN accounts for these so-called fingerprints that illustrate quite well how the sea level changes are different in different parts of the world. So now a few words about the theory behind SELEN. As you probably know, if you have looked already to the user guide, the theory is not really very new. It dates back to the classical work of Farrell and Clark, who introduced it in 1976 the basic features of the sea level equation. The paper is written in a different language with respect to the user guide, but the physics is basically the same. So when we deal with the sea level equation, the basic unknown of our problem is S. S is relative sea level change means sea level change relative to the solid surface of the Earth. And in particular, I would like to stress that this sea level change is only that component due to the glacial isostatic adjustment contribution. As you know, sea level variations are also due to other processes like steric warming of the oceans and so on. And these components are not included in the code, which is only oriented to GIA, to glacial isostatic adjustment. So technically, the sea level equation is an integral, linear, three-dimensional equation, which is somewhat similar to an inhomogeneous one-dimensional freedom equation of the second kind. And this equation, as you know, is solved traditionally by iterations. And although SELEN is a three-dimensional equation and not a one-dimensional equation, the same method will be applied to solve this equation. It is not a differential equation, it is an integral equation. So the integration domain will be spherical because we are concerned with the global problem, which is sea level change. Of course, we cannot reduce the problem to a local or a regional problem. So we will use an integration domain which is spherical, and we will take advantage of a discretization based on a icosahedron geodesic grid taken from astrophysical studies. We use a pseudo-spectral approach, means we use a spherical harmonics approach to solve this kind of equation. Also, this is taken from the literature, in particular from the papers of Peltier and Mitrovica in the 80s. The time integration will be fully explicit because our time dependence will be governed by analytical functions. So the harmonic function will be are introduced in the code by means of the SH tool developed by Mark Victorek in Paris, and we will use throughout a complex, fully normalized spherical harmonics, which are very convenient for our purposes. So I would like to list a few limitations of the theory and consequently also of the program SELEN. Some of these limitations can be relaxed in the future. We will go back to this at the end of my talk. And the first limitation is that the Earth, the solid Earth, is assumed to be incompressible. That means all the layers have a constant volume, and the volume of the total volume of the Earth will not change during the glacial isostatic adjustment. The rheology is Maxwell linear, and in particular, it is important to stress that the theory is not dealing with three-dimensional rheological variations in the lithosphere. So it is basically what we are solving here. It is basically a one-dimensional problem along the radius of the Earth, and the rheology is Maxwell. And in the future, it is possible that it will be extended also to other linear rheologies in future releases of SELEN, possibly. Another important limitation for the moment is that there is no rotational feedback on sea level, so the Earth is non-rotating, and we are not including effects from Earth rotation, consequently, on sea level variations. This limitation is going to be relaxed in the future versions of SELEN because the rotational feedback on sea level change is a quite important factor. Here, the coastlines are not allowed to migrate horizontally, means that the shape of the shorelines of the coastlines will remain the same as sea level is changing. This is another important limitation that can be relaxed in the future. All these limitations are perfectly consistent with the theory of Farrell and Clark. So actually, SELEN is exactly solving the sea level equation in the form proposed by Farrell and Clark in 1976. An important limitation again is that there is no coupling between the ice sheets and sea level change. Okay, that's an important physical part that it is not included in this sea level equation solver. And finally, only GIA effects on sea level are modeled, as I have mentioned before. So no other sea level variations, sea level processes are modeled in this approach. So what is the shape of the unperturbed Earth model that we are using in SELEN? That's a sketch showing this unperturbed Earth model, a spherically symmetric Earth, in which the elastic parameters like the Lamech constants, mu, and lambda is infinity because the Earth is not compressible, mu is only changing with radius, so with the distance from the center of the Earth. The density as well is only changing with radius, and it will be constant since, again, the Earth is not compressible. The Newtonian viscosity as well will be only a function of the radius, eta, in this cartoon. And in every layer within the mantle, we assume a Maxwell rheology, means that we account simultaneously for elastic deformation through a hook element, which is representing an elastic rheology, a perfectly elastic rheology, and we account also for viscous effects through this Newtonian damper of viscosity eta. So all the layers will have this kind of rheology, but of course the parameters described in the rheology means the viscosity and the elastic rigidity, E is equal to mu in this slide, will change with the depth in order to fit some realistic seismological model, if you want. So what is the sea level equation essentially? The sea level equation is a tool for describing the time variations of the red segment that you see in this cartoon. This red segment is separating the sea surface, if you want the geoid, the blue line here, from the solid surface of the Earth. So these two surfaces will change in response to eye thickness variations, the blue lines here, and this time depending sea level change here will be affected also by Earth rheology, which is represented by the usual Maxwell body in this cartoon. So actually the sea level equation says that S, the sea level variation, so the sea level variation is the variation of this segment here, will be given as the difference between the absolute sea level variations, which means the sea level change seen from the Earth center of mass, so the sea surface variation, the variation of the blue line relative to the Earth center of mass, minus the vertical deformation, means the displacement of the solid Earth in response to the changing sea level and at the same time in response to the changing eye thickness. The sea level equation, so apparently, is very simple. It is S at a given place omega on the Earth's surface and at a given time t equal to n minus u, where n and u have this meaning. The point is that this is only apparently simple because if we go to the details of the derivation, we realize that both vertical displacement and the sea surface variation will be a function of sea level change itself. So according to Farrell and Clark, we end up with this form of the sea level equation, which is the final form which is solved by SELEN, in which you see that S, the sea level change, is at the left-hand side of the equation, but it is also embedded in three-dimensional integrals on the right-hand side. The overline here means ocean average of these three-dimensional convolutions. Rho I and rho W are the density of the ice and of water. GS is an important function for us here. It is the sea level green function, means the function that describes the response of the Earth to a unit load acting on the surface. These symbols are convolutions over the ice load and over the oceans. So there are three-dimensional convolutions, and two-dimensional is in space and one-dimensional in time. I is the history of ice thickness variation, and Mi here is the history of the ice mass variation. So it is indeed an integral equation that cannot be solved explicitly because S is both at the left-hand side and embedded in these strange three-dimensional integrals. But when we solve for S at the end, and this can be done using an iterative approach, when we solve for S, we have access immediately to the U function, that is, to the vertical displacement function, since I is known as given a priori and S is known from the solution of the sea-level equation. And after this, we can have also access to phi, which is the variation of the geopotential of the Earth associated with the sea level variations and with the time-dependent ice load. These two convolutions involve two different green functions, one for vertical displacement, the other for the gravitational potential. It is important to discuss a very particular component of the sea level equation. This term in the middle here, this term is called SE, and the name of this term is Eustatic sea level change. Eustatic sea level change is a solution of sea level equation when these four terms are dropped. That means when the green function is zero. That means when we completely neglect the deformations of the Earth and the time variations of the gravitational attractions between the solid Earth and the oceans, between the oceans and the ice sheets, and between the ice sheets and the solid Earth. So this eustatic sea level variation is important because it is appealingly simple, but it can only be obtained when the Earth is simultaneously rigid and when the gravitational attraction between the various components of the Earth system are completely neglected. So in this case, the green function are zero, and the sea level equation reduces to this explicit equation that shows that S is only dependent on time through the time variation of the mass of the ice sheets. This is a very particular equation stating that the sea level changes are the same everywhere. So we term this solution eustatic solution. An important point about the eustatic solution is that if we take the ocean average of the spatially dependent sea level variations, we obtain exactly the eustatic solution. It means that in the general case, the sea level variations are not eustatic at all, but if we take the global ocean average of these variations, we get exactly what we have called the eustatic solution, which is a particular solution of the sea level equation. So, what do we do in order to solve this sea level equation? We use a pseudo-spectral approach, which is greatly facilitated by a sort of trick in which we transform the sea level equation in another equation where the convolutions are computed not only on the places where the ice is located and on the oceans, but on the whole Earth surface. And this greatly facilitates the numerical approach, means that in this case we can approach the solution using global spherical harmonic decompositions. So we define a modified sea level change Z, like the product between the ocean function, which is a constant here because the shorelines are not horizontally moving, and the ocean function is a function that is 1 when you have wet pixels, you are in the middle of the oceans, and is 0 if you are on land. So with this simple trick, we can get a sea level equation in the form of Z equal to something that depends only on the ice distribution plus ZE, which is O times S eustatic, plus a function which is a function of Z itself. So that's the equation that the SELEN is solving, actually, but the solution is performed in the spectral domain by using an iteration, because the sea level equation is not an explicit equation, it is an integral equation, which we can only obtain a solution after some kind of iteration. The iterations are starting with an initial guess, which is the eustatic solution, that solution which is true on the average, and the other iterations are defined in this way. Normally, from our experience and from the literature, we know that after a few iterations, 3 to 5 iterations, this will converge to the solution of the real sea level equation. Once this is done, we obtain all the variables in the time domain, in the spatial domain, by synthesis on the spherical harmonics, of course. So, configuration and execution, just a few words on these two important aspects of this presentation. First, a look on the structure of the directory of SELEN. It is a very simple structure. Here you find the most important file names and folders. Data, for instance, will contain SELEN supply data sets, in particular quantities which are important for the computation of the lab numbers. You will have some information about the location of relative sea level sites that are useful for our test run in a few minutes. And ice models will be in directory devoted to collect the ice model data files. So information for the time evolution of the ice models. The depots is a folder that collects all the outputs of SELEN after a given run, and the depots will be named depot xxx, means some name given by the user. In the input, you can supply pre-computed input data sets, like larger sets of spherical harmonics that can be saved each time that you run the code. And you have a directory for the executables, directories for the object files, a directory SRC for the SELEN sources, and the TMP scratch area for SELEN execution. The most important file for our purposes here is the config.dat file here, which is the file that is used to make the configuration of SELEN. So in order to summarize the configuration file, we can say that this file is composed by two sections. The first one contains the general settings of SELEN. That means the user can define the approximation or mode of solution employed to solve the sea level equation. The user can also define the rheological properties of the Earth model. It means that he can choose the viscosity profile of the Earth and the values of densities and rigidities. And it can define the spatiotemporal features of the surface load. Means you can define or select, if you want, the ice model to be used in the numerical computations. In the second section of the configuration file, it is possible to perform a scheduling of the outputs of SELEN according to the exercise that is going to be solved by the user. In particular, it is possible to define a number of ASCII files and tables, plots and diagrams created by GMT at runtime, and all this information, which are the outputs of SELEN, at the end will be collected in this depot folder described a few minutes ago. So, two sections in the configuration file, and in each section we have several options, and the options are organized generally in test blocks, very simply. This is an example taken from a sample configuration file showing that options are given in this way, and we have active lines that are starting with a particular code, for example 150 here, and corresponding to this particular code we have an important parameter of the configuration file. For instance, in this case, the so-called Tegmark resolution. That means a parameter that defines the grid resolution used in the numerical integration of the sea level equation. So option values must be enclosed in single quotes, like 24 here, and all the other data on active lines are ignored and can be used for comments or annotations. And in each text block like this, number and data type of the options field will depend on the context. We will give examples of it, of course, in a while. So the execution of SELEN is in 3 steps, and the configuration script is first invoked by the command configure. The user can also provide explicitly the name of a Fortran compiler to be used for the execution using another form of this command. If no errors are found, SELEN will be launched by one of these 2 commands here, and using the make run command, which will compile the program units, will set up the working folder in the SELEN directory, and will launch at the end SELEN. So the execution is basically in 3 steps. In the first step, there is the pre-computation of gridded spherical harmonics and load deformation coefficients. A spatial grid will be constructed. The ocean function will be discretized. The ice thickness variations will be decomposed in spherical harmonics, and the spherical harmonics themselves will be computed at all the grid pixels. In step 2, the SELEN program will solve the sea-level equation by the pseudo-spectral method using the iteration that I have shortly described before. And all the spherical harmonic coefficients of the various geodetic variations like vertical deformation, sea level change, gravity field variations will be computed. And finally, using the spherical harmonic coefficients, all the geophysical and geodetic quantities scheduled by the user will be computed. And at the end of the steps of step 3, all these quantities will be organized in a ZDPOT folder. So we configure and run now a test run of SELEN, which is oriented to solve a quite standard geophysical problem. And this geophysical problem is described here. We want to calculate the response of the Earth to the melting of the late Pleistocene ice sheets, in particular assuming that the ice sheet will follow the so-called I3G deglaciation history introduced by Tashing and Peltier in 1991. So we will configure the code in order to produce a number of geophysical quantities, not only spectral quantities like load deformation coefficients, but also sea level variations at some given specific location, and also geodetic variations, and so on. And after showing the configuration here, we will run the code and parse the depot folder of SELEN in order to visualize and shortly discuss the outputs for this particular configuration. So now I go to the configuration of the first part of the configuration file, in which we must give the SELEN settings for the test run. And the first setting is a purging option that can be used to remove auxiliary files from the working directory before SELEN is executed. And this is particularly useful in the case the previous run of SELEN has crashed, possibly leaving some files around. So this purging option is the first option in this section 1 of the configuration file. The second step is defining the mode of solution of SELEN. SELEN can run in the so-called gravitationally self-consistent mode. That means in the full form you have seen before, but it can also be solved in some simplified configuration in which we only account, for instance, the case of 2, in which we only account for the elastic deformations. We neglect completely the viscous deformation of the mantle. It can be solved in the so-called Eustatic approximation, in which it is assumed that the Earth is completely rigid, and so on. And there are also other 2 particular configurations that are not described in my slides. You can have a look in the user guide if you want to have information of this. So in this exercise, we will solve this, of course, in mode 1. That means since we are doing a realistic geophysical exercise, we want to solve the gravitationally self-consistent form of the sea level equation. And with, sorry, see an error here. We are asking 3 iterations. This 3 here means 3 iterations, not 5, like I written here. Means that we decide to stop the iteration only after 3 steps. That is usually okay in order to solve correctly the sea level equation. So after this, we have a configuration section that is about the resolution and the grid that is necessary in order to solve the sea level equation. The first option is about the maximum harmonic degree of the analysis. Lmax, in this case, is set to 72. It is not a very time-consuming computation in this case, because 72 is a moderate number of spherical harmonics. The analysis will be always in the range between 0 and Lmax in the sea level equation solver. We can choose the reference frame, means that we can decide to stay in the center of mass reference frame, setting CM here, and we can, or alternatively, we can decide to stay in the center of the undeformed Earth. The most physical choice is the first one, so we stay in the center of mass of the whole Earth, solid Earth plus oceans plus the ice sheets. And we set the grid resolution parameter R, that is useful to fix the detail of the ocean content distribution. Given R, we have a given number of pixels, which is basically given by NP, 40 times R minus 1 plus 12. That comes from the icosahedral pixelization of the sphere that we are using in SELEN. Of course, the area of the grid cells will be inversely proportional to the square root of the number of pixels. We can also set a name for a table containing all the pixel coordinates. In this case, we use this name here. That is useful when you don't have already a table available. So the first time that you run the code, you need to have a new file name for this kind of table. So that's a sketch of the grid that we are using in this case, corresponding exactly to the R parameter that we have set for this example. As you can see here, we are using this grid, which is icosahedron-based geodesic, borrowed from astrophysics. It is a quasi-regular grid that makes the computation of spherical harmonics really straightforward. It is really amazing to see how this grid is useful to solve this sea-level equation. So, fourth part of this setting section of SELEN, or the rheology section, we must choose the Earth model, and in this case we can use a couple of parameters. First of all, we can set the number of viscoelastic layers to be used. In this case, we have a model with 2 viscoelastic layers, NV is equal to 2, an upper mantle and the lower mantle, and a code. The code is another parameter that defines the rheological profile, that it is used for setting the density and the rigidity profiles to be employed. And in all the models available through SELEN, the lithosphere will be elastic, so we will not have any viscous response of the lithosphere, and the core will be homogeneous and in V-sheet, so there is no inner core, the core is simply homogeneous. So, for instance, if you look at the code of SELEN, you will see that it is possible to set NV according to values ranging between 2 and 9. So in general, the layering of the mantle is quite coarse in SELEN, but this can be improved, of course, working on the routine that is generating the lab numbers. For example, in the case NV equal to 3, that is not the example that we are adopting in this test. You may have 8 different combination of density and rigidity profiles coming from the literature, basically. So important models that are published in the literature can be used to work with the sea-level equation. In our case, I'm going back to the previous slide, I'm using a 2-layer mantle, so it is a very simplified rheological profile. You should, in order to have to visualize the values of the rheological parameters, you can have a look to the log directory of the depot folder, where you will find the log of Taboo. Taboo is our log number calculator, which is summarizing the values of the radii, of density, of rigidity, and of viscosity used for a given test run, like this one, for instance. So, ice model. The ice model is chosen using this part of the configuration file. Here we decide to use ICE3G for this test. And for this test, ICE3G has a time step of 1 kilo-year, and that's basically the natural time step for this kind of models using in glacial isostatic adjustment modeling. And we ask SELEN to build a new spherical harmonic ice file, whose name is written in this option 171. Just to give an idea, that the distribution of ICE3G, the model that we have selected for this kind of test, as the last glacial maximum, means in this case 18 kiloyears before present. As you can see, the structure of the model is quite clearly made of disks. The disks are really useful elements because the spherical harmonic approach to the decomposition of the ice load is really made very, very simple using these symmetrical kind of ice elements. As you know, probably, using SELEN, you have access also to other ice models. You can have some ad hoc ice models that are disks or cap-shaped one-element ice sheets useful for testings and so on. But you will have also access to ICE1 and to ICE5G models, which are important models taken from the literature. In this case, I remind you that we will use ICE3G. As you can see from this table, you can also use individual components, regional components of ICE3G, which are listed here. For instance, we have components for Antarctica, for the Baltic region, and so on. And this is sometimes useful in order to have some kind of regional analysis of sea level changes. So, spherical harmonics here, we decide to decompose, to compute the spherical harmonics over all the pixels using this command here, and we give a name to this binary file that can be used also for other computations in which the resolution parameter and the Lmax parameters are the same as in a previous computation, in order to save time for the next computations. Finally, point 7, the ocean function. We decompose in spherical harmonic the ocean functions here, and we save the harmonics for future computations in this file called ofl72.dat. And last step of this, that's the ocean function actually. That's the ocean function in the physical domain before the decomposition in spherical harmonics, just to give an idea of what the ocean function is. Final step, we define the name of our repository file folder. In this case, the name is test. After the execution, we find all the outputs of SELEN in this folder for inspection and for analysis, and giving, of course, the same name. The second time you run the code will cancel all the previous files. So in any case, be careful with this name of the depot folder. So after this first part of the configuration process, we go to the second part, which is much shorter. In the second part, we must decide what we want to compute from SELEN. And in this exercise, we have decided, first of all, that the execution of the GMT scripts will be switched off. So we will, after the execution, we will move through the folders in order to run the GMT scripts, in order to build maps, tables, and so on, showing the results of the test. This is quite useful because in this case, we will save some CPU time at runtime, and after the execution, we can go in the directories that we are very interested in, just to run the GMT scripts that are useful for our analysis. We also decided that we want the maps of the pixelization, just to have a look to the grid we are using. We want also a map showing the ocean function and its harmonic reconstruction. For the ice model, we want the maps of the original sheets, and we want also a plot of the equivalent sea level. That means the time history of the volume of the ice sheet. That is useful to understand how the volume is changing through time. We want plots of the load deformation coefficients, and in this test we ask also for some sea level prediction at the sites contained in the file sealevel.dat in this test. And for these sites, we want to have individual plots of relative sea level curves, after having also some plots showing the distribution of these relative sea level sites. We want some scatter plot showing the data compared with the prediction at each site. We don't want any regular relative sea level analysis, but it is possible to do that with SELEN if you want in another test run. And we don't want any computation at the tide gauges. This is left for another exercise later on if you want. And most importantly, at the end, we would like to have some snapshot of the fingerprints of sea level change, of vertical deformation, and of the absolute sea level change, which are useful to appreciate the spatial variations of sea level change due to glacial isostatic adjustment. So we have decided not to perform any geodetic prediction at locations possibly listed in this file here. We don't want it. We don't want regional rates of sea level variations and so on. And at the end, we want an analysis of the gravity field coefficients or variations associated to glacial isostatic adjustment. That is useful if you want to make comparison of your result with, for instance, GRACE data that are in fact providing the rates of the gravity field variations through time. So that's the end of the setting of the configuration file. We now parse the folder of the outputs in order to run the scripts useful for the visualization of the outputs that we have scheduled. So before doing that, we must run the code, of course. With configure, we make the configuration of the program, and we will have on the monitor some lines that are summarized here, and some messages, which usually means that everything is going well. After this, we make the run of the code, and you will have a flow in the screen, and the last line will be a statement saying that the output will be available in the depot test, in this case, because test is the name that we gave to our depot at the beginning. So now we run the code virtually, and we go to the directories in order to visualize the output. We go to the working directory /depot/depot test, and we go to px. Doing so, we can run this script here, pxmap.gmt, that is useful to visualize the grid in several ways. You can have on the right of this slide the different plots for the wet and the dry pixels, means the ocean and the continental pixels. And on the left, you will have a plot showing the same in a spherical perspective. Each point, of course, is the center of a grid cell according to the discretization introduced by Max Tegmark in 1992. So if you go to the OF folder of the depot, we can manage the OSM function. We will generate, in this case, with OF.gmt, two plots showing the original OSM function. That means the theoretical OSM function defined as usual in this way, 1 over the oceans and 0 over the continents. But we can also play with the reconstruction of the OSM function, as you can see on the right hand. On the right of this slide, you see the reconstructed ocean function in degree 72. Of course, you don't get exactly the original one. You get an image which is only a reconstruction of the ocean function. That gives already an idea that, after all, even if the number of harmonics is quite limited here, you get a quite reasonable ocean function at the end after reconstruction. So going to the depot of the ICE3G model, we can build the maps at each time step, maps of the ice model. Previously, I showed already the maps at the last glacial maximum. In this slide, I'm showing the map at present time. So that gives an idea of the time variation of the ice thickness. And we can also reconstruct the shape of the ice at degree 72, running this reconstruction script that uses GMT to produce these maps here. The time history of the ice volume here, it is interesting to see that the ice volume for ICE3G is following this kind of behavior. it is constant until 18 kiloyears before present, then it decreases almost linearly with time until 5 kiloyears before present, and it remains constant to present time. Equivalent sea level will be given by this ratio here, so the plot of the ice volume can be directly translated into an equivalent sea level, but this equivalent sea level is not actually the sea level variations that you observe due to glacial isostasy, because this ESL parameter gives an idea of what you would observe in the case of a rigid Earth, in which sea level variations are the same everywhere. So you can also plot the load deformation coefficients. Probably I'm running a little bit late, and here I go back to the theory. The theory says that there is a direct connection between the green functions and the H and K love numbers. Using SELEN, you can plot the elastic and fluid love numbers as a function of harmonic degree. And this is done in the love numbers by taboo folder. Running the script ldcs.gmt, you will obtain the relaxation spectrum, means the relaxation times of the Earth model that we have chosen before, and also plots showing the elastic load deformation coefficients and the fluid load deformation coefficients as a function of harmonic degree. Of course, with increasing harmonic degree, you will have a decreasing wavelength, and so these plots are useful to understand the spatial scale of deformation and the time scales involved in the process of relaxation. So something about geophysics now. We have decided to run the test run for this set of relative sea level sites. Each dot here is a place from which we have information about the history of relative sea level. And using this script here, you can generate this map automatically after the end of execution. And for each site here, you can have a plot showing the data available from the Tashinger and Peltier database. The data are shown here like with error bars, and the predictions obtained running SELEN by a thick line here. Here I have taken only 4 examples. One is from the Richmond Gulf. One is from oh, I cannot read this name here anyway. The third one is from Lübeck in West Germany, and the last one is from Belize. As you can see, the 4 curves have very different shapes, and that's a consequence of the Earth deformation, of the gravitational interaction between the ice and the Earth, and so on. You can put all these things together, comparing the scatter plot of the observations with the scatter plot of the predictions. It is only qualitative comparison, but you can see quite well that there is a good agreement between the two things. If you're not satisfied with the agreement that you obtain in this case, you can go back and run again the code, changing the viscosity profile, for instance, or changing the shape of the ice and the time chronology of the ice. Finally, I can skip this. Finally, I can show the sea level fingerprints here. The sea level fingerprints can be generated going to the Gmaps subfolder of our test folder and running the script gmaps.gmt. What you see here is the sea level fingerprint associated with the glacial isostatic adjustment, showing the rate of sea level change that we would observe today only with GIA. And you can see very well that the sea level change is not uniform everywhere. It is large and negative where there was a thick layer of ice at the last glacial maximum. It is larger positive in the periphery of these thick layers due to the subsidence associated with the collapse of the 4 bulges after the end of melting. So you can do the same with the other 2 fingerprints. That's the absolute sea level change fingerprint. That means the sea level variation seen from the center of mass of the Earth. And you can also do the same with the vertical displacement fingerprint. Of course, the first map I have shown by the sea level equation is the difference between the second and the third. And These maps are beautiful because you can appreciate directly the physical response of the Earth, but you can also perform with SELEN a spherical harmonic analysis of this map. And in this case, we have scheduled the computation of the rate of change of the Stokes coefficients. That means the gravity coefficients of the Earth, which are the harmonic components of the absolute sea level change map that we have already seen before. And doing this kind of analysis, you realize what the impact of GIA is on these time derivatives of the Stokes coefficients. That is useful sometimes if you want to make a comparison with space geodetic missions results like a GRACE, for instance. So, what's next? I think that SELEN 2.9 can be greatly improved, and in the future we are planning to introduce the rotational feedback on sea level in the SELEN 3, which is probably our next step. We will introduce also coastlines, which are allowed to migrate horizontally in consequence of sea level change. And importantly, we will also introduce present-day scenarios for the melting of continental ice sheets, such a way that you will be able to model the effects of the present-day melting of the ice, like ice sheets like Greenland and Antarctica, on sea level variations observed on a secular timescale that are important indeed, like they are important those shown here today, which are the effect of the response of the Earth to glacial isostatic adjustment from the melting of past ice sheets. So I think that's all. Thank you very much, and have a nice day.
Thank you very much, Giorgio, for taking the time out this evening and introducing us in a very nice webinar that really clearly laid out SELEN and its capabilities. I really look forward to seeing more of the science that comes out of using this code. Everybody, if you have any questions, please go ahead and type them into the chat window now. I have one question for Giorgio. I was wondering what platforms you're running on this code on, and about how long do our runs expect to take?
Oh, okay. Basically, SELEN can run in all the Unix-like platforms, and but it can also be installed in on Windows using Cygwin, actually. So the second part of the question was about the execution time.
Correct.
Okay, so the execution time is strongly dependent on the resolution that you are employing for your computation, of course. So, I mean, our experience is that running the code in I mean, standard laptop, you can have beautiful results in something like half an hour if you want to run a fully realistic geophysical simulation like I did now this evening for you. It is not very time consuming, but of course if you want to have a very high spatial resolution, you should consider that the execution time will increase with the square of the maximum harmonic degree of your analysis. So it will take some time at the end.
In your output files, do you are there files that state what the default parameters are if we don't specify them in the input files?
Sorry, I don't understand your question.
So I believe in the beginning of the talk we were going through the input parameters that we can set in the config files. Yes. Similarly, is there an output file that specifies what parameters were actually used in case yes. Input parameters weren't specified?
Yes, in the case that you are planning different runs with the same harmonic resolution, let's say, you can save the first binary huge files that you get containing all the spherical harmonics for another run in which probably you are asking for different geophysical outputs. For instance, you can save the files and run the code using two different sets of relative sea level sites. And in this case, you can take advantage of a pre-computation indeed. That's very useful in order to save time.
Great. Does anybody else out there have any questions? While you're typing that in, I want to remind people there will be no webinar next month because we'll all be at AGU. Our next webinar will be on January 9th and will feature Dr. Oliver Krylos from UC Davis, who will talk to us about advanced visualization. For all those who are going to AGU, please come by and stop by our booth. We are on NSF Street. And also come to our annual business meeting and network with the rest of our SIG community. We'll be meeting at the Park 55, our usual spot, on Tuesday evening, December the 10th. With that, I don't see anybody typing. Thank you so much for Giorgio for that great webinar. We hope to see you sometime stateside soon.
Thank you very much.